Okay, so in this video, we're going to start about quantum field theory. So, what is the need for quantum field theory? Okay, so we'll have to tell you what is the motivation why people worked out this quantum field theory. So far in quantum mechanics, we have never encountered a theory to handle the phenomena of birth and death of particles. Like when if in a particle collider, if you have an electron and a positron pair, they will annihilate each other to produce a photon. So here two particles are being destroyed and a new particle is being created. So a theory that requires to handle this kind of a phenomena had to be developed. So that was the motivation to for the birth of quantum field theory. And uh, Sidney Coleman, one of the uh, giants of quantum field theory, he said that as a theorist, as a theoretical physicist, as you progress, your ability to handle the linear harmonic oscillators or the harmonic oscillator in increased levels of abstraction is what requires of a theorist. So the entire so one of the prerequisites, okay, so one of the pure prerequisites to study quantum field theory is the linear harmonic oscillator in or the harmonic oscillator in solving the harmonic oscillator by the ladder method, something called the ladder method, or it's called the creation and annihilation operator. So we'll come to see what they mean. Okay, so we'll come to see what they mean. So let's start with that. Okay, so we're just going to build up with some prerequisites and then we'll go into actual field theory. Okay, so quantum field theory. So this is one of the prerequisites. So in we have studied about how to solve the harmonic oscillator in quantum mechanics, so you can look that up. Our videos are there. So one of the things is to write the any quantum mechanical problem, you have to solve this equation, right? This is the Schrodinger equation, right? So this is the Schrodinger equation. You have to solve this time independent Schrodinger equation. This is your operator, right? So this is your operator. It is your Hamiltonian, right? It is your Hamiltonian. Hamiltonian is nothing but the total energy. Okay, so the total energy, and it is written in terms of operators. So remember, all xp are written in terms of operators in quantum mechanics. So if you don't know what that is, we have a series on quantum mechanics, so you have to go through that before you get here. So this is operator we will call, and this is operating on a eigenfunction psi, right? So this is your eigenfunction, and it drops a eigenvalue, right? So it drops so this is the eigenfunction. So an Hamiltonian operator acting on an eigenfunction produces a eigenvalue. Okay, so this is the eigenvalue. So the eigenvalue gives the corresponding correct energy. So eigen meaning it's the correct energy value for the this eigenfunction. Okay, and reproduces the eigenfunction. Okay, so this is an eigenvalue equation. So if you don't know again what an eigenvalue equation means, the best place to learn it would be in when we in our series we've done about matrices and eigenvalue equations. Okay, the Cayley-Hamilton theorem and all those things. So that would be probably a good place to learn it. So this is what it does. So now we'll have to write the Hamiltonian. So the Hamiltonian total energy is p square by 2m. P square is your momentum operator, right? So the momentum operator plus half kx square. So this is the Hooke's law potential, right? So this is your Hooke's law potential, right? So now this is your Hamiltonian, the kinetic energy term. So this is the kinetic energy term, and this is your potential energy term, Hooke's law potential, right? So Hooke's law potential. So now this k we can write as in terms of omega using this relation. Okay, so therefore I will write this as p square by 2m I will pull the 2m out of brackets. Right. P square m. So this is your Hamiltonian. Okay. Now notice, remember, we wrote out a commutation relation between x and p, right? You remember we had written a commutation relation between x and p, and we evaluated the commutator to be I h bar. So the commutator is just the how, if you compute x bar and p bar and reverse the order and compute p bar and x bar, what will be the difference, right? This is the value of the commutator. So these operators find out the expectation values or the eigenvalues, and if you commute, they will reverse the order and compute what will be the difference. So they don't commute. So generally, operators here we have these x and p operators don't commute, and they don't commute by this amount. So this is the canonical commutation relationship. So this is your canonical commutation relationship. Now I'm going to define certain operators. So I'm going to define certain new operators, which I will call a plus and a minus. Okay, so I'm going to define these operators a plus and a minus. So if this notation is new to you, I'll tell you how you ought to read these equations. Okay, so this is a new definition we are introducing. Okay, the new definition we are introducing. So how we read this is the top sign. Okay, so a plus is this term, and you read a minus sign here when you're reading a plus. Okay, and when you're reading a minus, so these are two equations combined into one. The top row reads as one equation with the signs on top, and the bottom row reads as one equation with the signs on in the bottom. Okay, so these are two equations combined into one. So the uh, the guarantee of defining this, I'll tell you before we get into that. I'll tell you what is the use of defining this kind of a operator, this a plus and a minus. Okay, what is the use of defining this kind of a operator? Now the use of defining this kind of an operator comes in when this was our eigenvalue equation, right? H bar. Now when you operate a plus, okay, let's say we are operating a plus on this wave function psi. Okay, let me give myself this a plus on the wave function psi. What you get is you get that the energy is incremented by h omega. Okay, the energy which was originally E is incremented by h omega. Okay, it is incremented by h omega, and you get the same eigenfunction again. And when you operate by a minus, the energy is decremented by h omega. Okay, so here you have the energy decremented by h omega. So here you can immediately see the kind of interpretation that this notation or this definition of operators a plus and a minus warrants. So here you can consider a ladder, a sort of a ladder. Okay, a sort of a ladder. So remember that the energy of a linear or for harmonic oscillator, linear harmonic oscillator is given by n plus half h omega, h bar omega, right? So n plus half h omega. So if this was, let's say this was your energy level, okay, this was your some kind of energy level that you are there in. So if you apply head a bar, okay, so a plus to this, okay, if you apply a plus to this, you increment this energy level by a factor of the difference in the factor is h bar omega, right? So you go to another high level, another one plus quantum state of energy. So here you increment by a factor of, let's say you come to, if this was n, you come to n plus 1, okay. So keep in mind this n is the quantum number n. So you come from here to here, and if you apply the lowering operator to here, you come minus 1 drug, okay. So in the ladder you come minus 1 drug by, and the difference again is minus, again the difference is h bar omega, okay. So here you can see that this immediately warrants an interpretation that where we can say that supposing you apply a plus to a, or a plus to a eigenfunction an, it increases its eigenstate by n plus 1, okay, and produces a factor eigenvalue n plus 1, okay, produces a eigenvalue n plus 1. And if you if you apply the lowering operator to this eigenfunction n psi of n, it decreases the value by n minus 1 and produces the eigenvalue n, okay. So here you can see that we are developing an apparatus, a theoretical tool or an apparatus or a framework to handle the creation and destruction of particles, okay. So this is going to be called your, creation operator, and this is going to be called your annihilation operator, okay. So this is going to be called your annihilation operator. So this is called your annihilation operator. So now we can write the Hamiltonian also in terms of these creation and annihilation operators. So the Hamiltonian written in terms of the creation and annihilation operators can be written this way. And now I have to tell you what guarantees this writing of the creation and annihilation operators this way and defining the Hamiltonian in terms of the creation and annihilation operators this way. So from our definition, so this is where we started out, right, with our definition. So from our definition, let's write out the x and p in terms of creation and annihilation operator, okay. So that is what I'm going to do now. So I'm going to write x and p in terms of the creation and annihilation operators and tell you, I'm not going to go too much into the detail of the calculation, but we're going to, in this course, we're going to concentrate more on the conceptual part so that you don't get lost in the detail, okay. So that is the challenge of teaching quantum field theory, that for any teacher of quantum field theory, there is a lot of detail in the calculation, okay. So it is easy to get lost in the detail, the calculation, and get lost out by the grand narrative that comes out of it. So we'll concentrate on that, and we won't be we'll stick to a theoretical minima, okay. In this course we'll stick to a theoretical minima, and we'll suggest books that you might need to go through to fill in the gaps of the calculations that we need to do. So just as I said, we have to write now, this is the x and p will write in terms of the creation and annihilation operator. So this is just the variable, two variables, and you have two variables x and p, and you have two equations, right? This is actually two equations. So you can solve for them and write x and p in terms of the creation and annihilation operator. So that's what I'll do right now. So what I've written out here is the x and p operators in terms of the creation and annihilation operators. So what guarantees writing the creation and operators this way is that this X and P, when the commutator is evaluated, it obeys the commutator relationship I H bar. So this is what guarantees our writing of our creation and annihilation operators this way. Now we're going to make a transition now into the next uh, development of the theoretical apparatus needed to enter quantum field theory. So we're going to consider these kind of springs, okay, these kind of springs continuously arranged this way. So we're going to consider all of space with springs aligned this way. Okay, so it's going to be like this is the continuously springs are aligned this way. And if this is the equilibrium point, we're going to consider small displacements from the equilibrium point to be some Qi. Okay, so some Qi, and each displacement we are going to sum it off as a going to write the kinetic energy term and the potential energy term for this. So for this so Qi is being summed over the summation I. So Q is being summed over the summation I to denote the displacements for all the springs from the equilibrium position. So this denotes the kinetic energy, and the potential energy is nothing but the Hooke's law potential, right? So for a spring system, it's going to be the Hooke's law potential, again given by K Qi, summation going over I Qx square. Okay, this is, so we're going to consider all of space is going to be filled with springs like this, linear springs like this, and what we're going to do is we're going to transition from these discrete variables, right, to a more continuous variable. So you might want to pay attention closely to the progression of thought here. So in order to describe the birth and death of particles, we are studying the harmonic oscillator in terms of the ladder operator method. We talk about creation and annihilation operators. So the creation operator creates a, we are going to interpret as if it's going to create a new particle, and the annihilation operator as it destroys a particle, because it raises and lowers the energy in the harmonic oscillator by one level. Okay, so now we are going to consider so many continuous, so we just considered one oscillator like this. Now we're going to consider so many oscillators, so many springs connected together, and we are going to consider them in terms of a ladder operator method. Now we're making another transition where we're going, here we are talking about a discrete system where we are talking about summing over summation I. Now we can move to a continuous system by changing it to a continuous variable psi. Okay, we're going to call it psi of x. It's going to be a function of x, and we're making the discrete. We're making the transition from a discrete to a continuous system. So discrete to a continuous system. Okay, so all the equations will correspondingly read in a continuous system. Okay, so now we're going to exactly reproduce the harmonic oscillator in this continuous system for the case of so many oscillators. Okay, so many oscillators. So here we consider only one oscillator. So here we're going to consider so many of the oscillators. So here we had written x and p, right? So x and p. So x was the position. Now this we will write now. So the position here we are taken to be q. Now we are taken to be psi, right? So this is going to be psi. So psi has to be written in terms of the creation and annihilation operators. Okay, so we're going to write in terms of the creation and annihilation operators. And remember, from now on we're going to use units where h bar is equal to c is equal to 1. So this is the system of units. So this is common in quantum field theory. So this is the system of units which we'll use. So now psi, which was our position, which played the role of our position. Now we're going to, which played the role of this q, the psi is going to be called your field variable. This is going to be called your field variable. It's going to be called your field, and this is written in terms of the creation and annihilation operators. And again, the momentum also has to be written in terms of, so for the momentum we will use a new symbol, pi. Okay, so this is going to be momentum here. Okay, so this is going to be momentum. We're going to call this as the momentum, and this will be called, so this will be minus I omega by 2. Okay, so this is again written in terms of the creation and annihilation operator. So again, what guarantees that this can be written this way is that it obeys the commutation relationship. Now we can, so I had said now this is written only for one oscillator, right? I had said now we're going to take, we have taken so many oscillators. So for each oscillator, we are going to produce a spectrum of energies. Okay, so we're going to produce a spectrum of energies. So here we were considering so many oscillators, right? So each oscillator can be oscillating with one particular frequency, right? So we will denote that frequency by this relation omega p, and it is related to the momentum and the mass by this way. Okay, this comes from your relativistic energy equation and from your system of units that we have defined, that h bar and c is equal to 1. So this is actually nothing but your relativistic equation, energy equation. Okay, so this comes from your relativistic energy equation. Now, therefore, I will write this, what I wrote down here, I will say this is for one energy omega p, and for it to denote so many oscillators with different energy levels oscillating with so many different modes of energy, I will integrate this. Okay, so I will going to integrate this with respect to, so if we are doing in 3-dimensional space, we'll do a 3-dimensional integral here. And AP. So again, so here you have, I'm writing the the creation and annihilator operator again. Now for each mode, okay, each mode omega p. So for each mode here I've written omega p, each mode we're going to have its corresponding creation and annihilation operators, right? So we're going to have these creation and annihilation operators. So this is plus, so omega p, right? Written out here. So this is going to be plus, and this is going to be the minus one. So the creation and the annihilation. And what I'm going to do is I'm going to Fourier expand the modes. Okay, so this is, if you learn about Fourier transforms, so you might be familiar with this. So this is the, so this is your Fourier expansion of your complete energy spectrum of your this is going to be called your Klein Gordon field. Okay, so what we're doing is actually quantization. This is called the second quantization. So this is actually the quantization of your Klein Gordon field. Okay, so this is the Klein Gordon field. And similarly, we'll have to do a similar thing for the momentum. Okay, so the conjugate momentum. Okay, so x and p are conjugate variables, right? So phi, the field variable, and phi, the field variable, and pi, the conjugate momentum to the field variable, is going to be, they're going to be conjugate variables. Okay, so they're going to be conjugate quantities, phi and pi. Okay, so this is your conjugate momentum. So again, I'll have to do a similar thing for the conjugate momentum. So write as omega p here for the denote the mode, and then I'll have to do the integral, and then I'll have to write the creation and annihilation operators. and the Fourier expansion of the modes. So this is going to be important. Okay, so what we've done is the second quantization, okay, of the Klein Gordon field. Okay, so you read, I will just write it out here. We've performed the second quantization. It's called quantization because now we have introduced the linear harmonic, the harmonic oscillator, which has quantized energy levels, right? So it has quantized energy levels because there is a integer n which quantizes the energy levels, and that we have introduced into the Klein Gordon field. Okay, so this is called the Klein Gordon for second quantization of the Klein Gordon field. Now, again, what guarantees this writing the this way is again that these the quantities obey the commutation relationship. So you can again check that this is guaranteed by the fact that we have the commutation relations obeyed here. Okay, so we have, okay, so that's that. So this is guaranteed by that these things obey the commutation relationship. So the how they obey, if you read up, probably if you read up Peskin and Schroeder is the most detailed book that has all the calculations involved. So I'm just giving you the conceptual background that you need to understand this complex subject. Okay, so now we're going to move transition into a next a little bit more on this Klein Gordon field and what we mean by these propagators. Okay, so what we mean by these propagators. Okay. So you might have you'll be familiar with the Dirac notation. We studied about the Bray and the Ket notation, the Bra and the Ket notation, where we write it like this, right? So we have the Bra and the Ket, and in the middle we put the operators, right? So here the operators are the fields themselves, right? So that is what we've done with the second quantization. Now here it just now the zero here, the zero and the bra and the ket don't denotes that this is the free field, right? So this is the free field where there is no external interaction. Okay, so that's what we denote by this zero. Okay, so now the when you we have denoted here two field variables x and y to denote that the distinguishedly denote that this is that the field points are different. Okay, that the field points are different. So what this when you work this out, okay, so when you work this out, you can work this out from what we've written here, changing the correspondingly for using correspondingly for the field variable x and y. You can work this out that this works out to be okay. So this works out to be this, and this is normally interpreted to be the propagator of a particle to. So this is called the propagator. So you must be familiar with these terminologies when you encounter them in your textbooks. Okay, so this is called the propagator, and this is interpreted to be the probability amplitude for a particle to propagate from y to x. Okay, so this is interpreted to be the amplitude for propagation. Amplitude for propagation. Amplitude for propagation. Okay, so now of course there is a you will encounter something called a problem of causality. Okay, because now the particles first have to be created before they are destroyed, right? That only will preserve causality, right? So they first have to be created before they are destroyed, because they cannot be destroyed if they are not created in the first place. So this will have to be written in terms of something called time ordering of operators. This is a way of placing the creation and annihilation operators. This is denoted by this time ordering of operators, and when they are done this way, this will give you the proper amplitude for propagation. And there are so many these integrals are not easily calculated. That is that the amount of literature that is there, that you will encounter in your textbooks, detailing how to do these integrals, amounts to most of the material in quantum field theory. Okay, so there is going to be, you're going to study a lot about regularizing these integrals, how people like Wick and Feynman did these integrals. So you can encounter all that in your textbooks. Okay, so I would probably recommend Peskin and Schroeder. So that is one of the leading quantum field theory books that are easily available. So this is, so what we've done is we studied about harmonic oscillator, right? So we started about the quantum field theory and how the creation and the destruction of operators can be denoted by the creation and annihilation operators of the harmonic oscillator. So we're talking about the harmonic oscillator in increased levels of abstraction, and we've come to study about the field theory. That we've started with the Klein-Gordon field and how to quantize it, introduce the uh, write the field variables in terms of the creation and annihilation operators of the oscillator, harmonic oscillator, and then we talked a little bit about what the probability, the amplitude for propagation and the propagators, what they mean. Okay, so we'll take this up in the, we'll develop on these themes in the next following lectures. So do subscribe to support this effort, and do share the word with your friends that something like this is happening.